For a couple of times now, I have addressed that in collision experiments, when both objects move in the same direction after collision, both draft science model and the conventional science model predict correctly. This is because when both objects move in the same direction, their momenta have to be added together. Now, according to conventional science, we only do this when they move in the same direction. And according to draft science, we always do this, regardless in which direction the object goes. Now, this is only the case when a bigger mass object collides into a smaller mass object. If a small mass object collides into a big mass, the small mass moves in opposite direction after collision, and that's where both models disagree. Now here is an example where both conventional science and draft science model predict correctly.
This little throw. Momentum 1 was, before the collision, was 0.127 for object 1. Object 2 had nothing, so the total momentum, both the textbook model and the alternative model would agree that the total momentum that we're starting with is 0.172 kilograms meters per second. And both the textbook model and the alternative model would agree with these because both of the carts were only moving in the positive direction. If everything is moving in the positive direction, then the textbook model and the alternative model actually give the same predictions. If everything is moving in the positive direction, then the textbook model and the alternative model actually give the same predictions.
Hooray! This proves draft science right, so this is a good experiment. Now here is draft science himself seemingly accepting and agreeing with the results.
Okay, so we can see that this did continue to move. Okay, so it still has momentum. So you can basically see that the blue cart that is almost half as light is not going almost twice as fast. So right there we've got a huge degrade in the amount of momentum it got. Okay, just gigantic almost. And we still have quite a bit though of energy left in the red cart. So the red cart didn't give all of its energy. It only gave a portion of it. And as he's going to state, if you really add all these up, it's okay. It's pretty consistent. You conserve the momentum. So the total momentum is conserved, because this kept going forward. Now, if it had reflected, then everything would have been a mess. But because the red card kept going forward, it means that it didn't give all of its momentum. That's why this isn't twice as high. And so you end up with pretty consistent numbers. Now, the catch is, for momentum, you conserve the momentum. The catch is, he doesn't tell you what the kinetic energy numbers are. And the fact is that the kinetic energy numbers come off 10%. All right, you lost 10% of the energy.
Well, here are the kinetic energy numbers. The initial moment of kinetic energy is 0.0264 joules. After collision, the one mass has energy of 0.0023 joules, and the other mass has energy of 0.0231 joules. That combines to 0.0254 joules. So that's only a difference of 0.0010 joules. Only a little loss of kinetic energy, which is always normal. There's also going to be some loss. Anyway, however, physicist Michael will now do the collision with a small mass into a big mass, and that's where the disagreement happens.
Taking some more data. We've got an object that is now moving in the negative direction. So just before the collision, well, there's only things moving in the positive direction. So both models would agree, if everything is moving in the positive direction, both models would agree the total initial momentum is 0.219, again, for both of those models. In the textbook model, momentum 1, we treat that as a negative momentum. So when we're adding these momentas up, I'm going to add up negative 0.036 plus positive 0.258. And I get from that I guess there's some rounding in here for the computer's model. I get around 0.221 or 0.222. Again, that alternative model claims that momentum does not care about direction. When we are adding up momentas, we're always adding up positive values. So in this case, we would have to add positive 0.036 to positive 0.258, and I get from that 0.294. That does not give conservation of momentum. The textbook model, well, within the noise, those two momentas before and after the collision, those match up quite well. The alternative model, not looking so good.
Now at this point, Draftscience will turn into the most crazy conspiracy nutcase where he will do whatever it takes to dismiss the evidence. He will call the experiment a garbage experiment. Every experiment with this scenario is either crap, cheated, wrong, or extremely flawed. Something must be wrong.
Updated that, and let's start taking some more data.
So now you got a bounce back. So now his claim is going to be this bounce back gets subtracted, okay, from this exchange, not added. Okay, and if you add it, it's too much energy. Now I would argue that clearly this is really high. So the argument could be made that this higher velocity, okay, of the lighter cart, in fact has more energy in the rotation of the wheels. This one has less energy in the rotation of the wheels, and that's making some of this up. But the fact is this one is way off momentum-wise. All right, there's lots of free momentum here, and but also the fact is if he pushes the kinetic energy button, it's also off. Okay, if you add the reverse direction, you end up being 10% too much energy, and if you subtracted it, you're 30% too little. So kinetic energy also failed to be conserved. So let's understand, momentum was not conserved, and neither was kinetic energy conserved.
Yes, momentum was conserved due to the negative direction, and kinetic energy was also conserved. Here are the numbers. As you can see, the initial kinetic energy is 0.0426 joules, and after collision, the total amount of kinetic energy is 0.0424 joules. Only difference of 0.0002 joules. I have no idea why you say it's 30% off. So it seems like you really don't pay any attention, or you just really suck at calculating. But kinetic energy was conserved as well. So stop lying. So to make up for the so-called free momentum, Draftscience is making the excuse that the extra momentum is stored in the rotational movement of the wheels.
So it's a latent or hidden momentum. So when the cart has a certain velocity in a direction, it's not telling you, the MV isn't telling you the total momentum because there's a bunch of momentum in the flywheel. So the faster the cart's going, the more momentum is in the flywheel, and the slower it's going, the less of its momentum is hidden. So a heavy cart can have a momentum that says, its MV is a little bit less, let's just say it's 90 instead of 100. But that fact is connected to the fact that it has received its energy from some other object where the wheels, of the other object are going faster. And so they had more momentum going in than you're going to get out because you're just seeing this motion. So the heavy object will look like it's going faster than technically it should because it got hit by more momentum than it appeared. So if I hit it.
Okay, so here's the logic of Draftscience. So first of all, we have, these are the numbers taken from physicist Michael experiment. So at part 1, small mass is 558 grams. The heavy mass is 806 grams. So this one is standing still to begin with initially. The initial momentum of the small cart is 0.218 momentum, right? That's what we can see. That's what we can measure. Then after collision, the heavy mass continues with 257 momentum, and the small mass reflects back with 0.036 momentum. Now, according to conventional science, we have to subtract these numbers. So 257 minus 36, that equals around 218. So momentum is conserved, but not for Draftscience, because we cannot use negative momentum. We have to add these two together. So the total momentum is 257 plus 36, which equals 293, which means we have 75 momentum is too much. This is free momentum. This is extra momentum. So now Draftscience will say, this 75 extra momentum is actually stored in the wheels as rotational momentum. And that we cannot see or we cannot measure. It's hidden. It's hidden momentum. So actually, the small cart initially had 218 plus a hidden 75 momentum in the wheels. So actually, this total momentum of the system is 218 plus 75, so 293. The initial momentum, the total initial momentum of cart 1 is 293. So this 293 collides against the heavy mass, and it gives away 257, and it still is left over with 36, but going in opposite direction. So that it works out for Draftscience. But hang on. This one, after collision, this also has inertial rotational momentum. The heavy mass after collision also has rotational momentum. The small mass after collision also has some rotational momentum after collision. It must be. So the thing that we can measure after collision is 257, but it also has some hidden momentum. Now I don't know how much. So let's say it's around 0.020-ish. That's just a guess. Let's take a small number, 0.020-ish. So it's what we can measure is 257, but it has some hidden momentum. So let's say 0.020. And then for the small part, the thing that we can see is 0.036, but it also has some hidden momentum, 0.010, for example. So now this total momentum becomes 257 plus 0.020, which is 277. And then this total momentum becomes 0.036 plus 10, which is 0.046. So now the total combined momentum of both cards is, so we have actually 277, the number that we can read, plus the hidden momentum, 277 plus 0.046. So again, the 36 plus the hidden momentum, that equals 323, but the initial momentum was only 293, right? That was the total amount of initial momentum, so 218 plus the hidden rotational momentum. So now we have to, so 223 minus 293. So actually we have to add another additional 30 momentum to the initial momentum. Because, so we have the initial momentum 218 plus the so-called free momentum, but then we have to take into account the extra rotational momentum for the card, the heavy card after collision and a small card after collision. We have to include that as well into the total initial momentum. So another 0.013, 30 initial momentum extra. This is kind of confusing, but I hope it makes sense. This is the logic. Now, when we reverse the scenario, instead of a small mass into a big mass, now we have a big mass colliding to a small mass. So we have the 558 grams colliding into the 308 grams. So the initial momentum before collision was 0.172. After collision, the heavy mass kept going with in the same direction with 0.051, and the smaller mass kept going or was launched with 0.119 momentum. When we add these two together, we have 170, which is very close to the initial momentum. Now, Draftscience, in this scenario, he didn't say anything about rotational momentum. He just saw the same numbers. All right, so we have around 170, 170. Okay, momentum is conserved, no problem. He didn't mention the rotational momentum. Whereas in the other scenario, when we have a small mass into a heavy mass, then we have all this, it's all about the rotational momentum stored in the wheels. He didn't mention anything in this scenario about rotational momentum stored in the wheels. Here is another example of a larger mass hitting a smaller mass. Once again, both cards move in the same direction after collision. So this is on an air track. The mass of card 1 is 300 grams. The mass of card 2 is roughly 200 grams, almost. The total amount of momentum before collision of card 1 is 0.118. The total amount of momentum after collision of card 1 is 0.026. And then the smaller card is 0.091. When you add these together, we have 0.116. So 1.118, 0.116 momentum is conserved because we have to add them together. So without taking into account any energy that is left in the rubber band, the rubber band still vibrating after collision, momentum is conserved perfectly. Only when both objects move in the same direction after collision, we always see the same numbers. There is no free anything, no free momentum. Here's another example of a large mass hitting a smaller mass. This time the larger mass has been increased with its mass. So we have lower velocities and another mass ratio. So this one is a 400 gram card colliding into a 200 gram card. The total amount of momentum before collision was 0.100. After collision, the large mass continued with 0.037 momentum. The smaller mass continued with 0.065 momentum. Add those together and we get 102. So 100 and 102 momentum is conserved. And so once again, it doesn't matter what the mass ratios are, doesn't matter what the velocities are. We have different velocities, different mass ratios, and we still have the same momentum before and after collision. Momentum is conserved. There doesn't seem to be any difference in the amount of energy still stored in the rubber band. Doesn't matter, the momentum are conserved. So here's another example of a large mass hitting a smaller mass. The large mass, the red card, has a mass of 520 grams. The blue card has a mass of 270 grams. We're going to see a diagram of the velocities. First the collision. Hold on, it's going to change. We have to watch until there we go. So here is the diagram. He's going to show the velocities. First of the larger mass, I believe. So which is 512 meters per second. And then, the initial momentum and after collision, it's 0.462 meters per second. And then after collision, the smaller mass card 0.658 meters per second. So now let me do the calculations for the momentum. Right, so the initial momentum was 0.266. After collision, the larger mass continued with 0.084 and the small mass continued with 0.177. Add these two together and you get 0.261. So momentum is conserved once again, 0.261 and 0.266, very close. The numbers are very close to each other, so which means that momentum is conserved for this experiment. And yeah, this experiment was with carts with wheels, so regardless of the amount of rotational momentum that it might have in the wheels, momentum is still conserved. There's no free momentum at all. So yeah. Now, however, the same person also did it the other way around, letting a 270 gram card colliding into a 520 gram card. In the past I have made an analysis video about this, so this is the video with my analysis of the calculations, and we see that the initial amount of momentum before collision is 1755, and then after collision the one mass reflected back with 0.0488 and the heavy mass continued with 2225, and momentum is only conserved when we subtract the numbers. When we add them together, then we have once again free momentum. So once again, every single time when both cards move in the same direction after collision, there is no problem for Draftscience model. Momentum is conserved. Also according to conventional science. However, when one of the cards go in opposite direction after collision, then it is in disagreement with Draftscience model. Then suddenly it's all crap, it's all cheated, it's all flawed, etc. So I just wonder, every single time when scientists let a large mass collide into a small mass, then it's good, there is no problem. Then they do not cheat the experiment, it's not flawed. Momentum is always perfectly conserved for Draftscience model. But the other way around, when they let a small mass collide into a large mass, then they manipulated the experiment and then they force the experiment to come out their way somehow. Then it's all a conspiracy, it's all cheated, it's all flawed, all crap, garbage, wrong. Something must be wrong, and so you blame it on the hidden momentum inside the wheels or whatever. So that's a contradiction.